All right. We reviewed our talk from what we call deep syntax. Me and Catherine will talk. So before the break, we talked about the shallow or implicit syntax using the CLSP, Kagar, or Chunker. Here we use the parser output. So the deep here means the using parser output or the reranking NP output. The justification of using parser is the intuition that grammaticality or good syntactic output or not can be measured by parser output in some sense. And we organize different features by the simple way of using parser output to more complicated way of using parser. So I'm going to talk about the simple way of using parsing output and also talk about model-based features. And Catherine will talk about dependency-based features. And after this session, Anup and Viren will talk more complicated way of using parser output. So the simplest way of using parser as a feature function is just use the parser score. Collins parser or other parser will are usually based on the statistical or probabilistic model. So it gives us the parser probability, which is generally the joint probability of the sentence and the parse tree. So Alex and Anup and others are working on this simple feature. Just take a log of the parser probability or divide it by trigram. Because parser output generally the joint, so we want to just think the tree itself. But somehow the simple way of using it is not good. So one experiment that Shankar did was just parse the reference sentences and produce baseline sentence and see how the parser probability is better. And this is a long probability of the parser output. So the reference sentence are supposed to be a good or grammatical sentence, but somehow the parser says the probability is low. So there are several ways of interpreting these numbers, but the sure thing is just simple use of the parser output is not that good. And the other simple feature is
does that result hold up if you divide by the trigram probability?
I'm sorry?
If you divide by the trigram probability, does that result hold up?
We don't know.
No. Still around the baseline. It doesn't get any.
Yeah, no, I meant the one on this slide. It just looks like grammatical sentences do worse rather than better.
No, we didn't try that. I didn't try dividing the
Not the reference experiment, but
for the reference
with the rescoring, they didn't do any better in rescoring.
Yes, I got it.
we didn't get. And the other simple feature function is more looking to the shape of the tree. So simple feature function is just count the tree depths or number of PPs or looking into right branching factor, because English tends to have more right branching. So I will show all the results at the end of my talk. And the second part of my talk is we also use the parser output as an input for different model. Here we use the syntax-based translation model, which are developed for their own purpose. So it was developed for as its own purpose. But the point here is we can the translation model is based on syntax. So we hope that this model probability will give more idea that if the translation pair is in grammatical sense good sentence, then it will give a higher probability. So what we did was apply the syntax-based model and calculate the model probability, and that probability is used as a feature value. And the syntax-based translation model itself has been studied for quite a period. Other work includes inversion translation grammar or helport model. And in this workshop, we use two translation model, which is tree to string or tree to tree. And those models are probabilistic model to give the probability how the parse tree can be converted to another parse tree or the string in another language. And within the model, there are several decomposition of the translation. And mainly they use the reordering or insertion or translation, or merging some nodes, or splitting some nodes, or cloning. So this is just an example how the parse tree of English is converted to foreign language, the reordering in the child nodes, or inserting extra words, and translating leaf words. Or tree-to-tree alignment model, we also have node merging. Or here, this is a input parse tree, and here we see a node merging, blue one, or node merging. And yeah, the red one is node splitting and reordering here. And cloning is also possible in a tree-to-tree model. The cloning means one of the subtree is copied to the other, to another node. And so because this translation model was developed for their own purpose, it is not always good for our n-best reranking business. Because an n-best list was produced by the empty system, and the empty system doesn't produce big word shuffle in the output. And also, we have concern that English Chinese has almost the same word order. So it may not be a good idea to use it. But some relative clause and other things have specific reordering. So we still hold some. And another issue here is the computation is very expensive. So we modified the implementation of the tree-to-string or tree-to-tree thing to force the alignment given by the empty output, or just use the short sentence in the empty list. And these models were trained separately. And because of the computational limitation, we only covered some amount of the n-best lists. And result here is the several different feature functions. So baseline is 35.6, and here we see simple feature functions. And tree to string or tree to tree also doesn't give much improvement. And here 32.0 was done by using more complex technique like splitting out big tree into small tree fragments. That will be mentioned by Anu and Viren. So much for it. So Catherine will talk about dependency tree-based features.
Catherine is the second of our three splendid representatives.
Don't see as charged. So I'm going to talk a little bit about how we use dependency trees in our projects, and just a little bit on the motivation of why we wanted to do this. Basically, there were two problems that we wanted to address with normal constituency trees, which is the direct parser output. So one problem is that the constituency trees can be unreliable due to the inaccurate parsing. So since, in this example which Dan showed earlier, there's actually no verb right here, but since the parser has been trained on grammatical sentences, it expects a verb phrase, and so inserts one right here. So if we were to compare these two trees, we might be misled to think that they are more similar than they actually are because we have a verb phrase here and a verb phrase here. So that's one problem that we encountered. Another problem was that a difference in tree depth could make finding a good tree-to-tree alignment difficult, even though two sentences can be syntactically similar. So if you look at on the left of each sentence, we have this cluster of nouns, And they're actually very similar. China, 14 open border cities, and translates basically to what you see here. However, on the Chinese side, going from the sentence node down to the lowest terminal, there's a level of 6 different, steps as you go down the tree. And in the English, there's only 4. So when the alignment program looks at these trees, it has trouble merging that many nodes together because there's a limitation in how many nodes can be merged at one time. So will assign a very low probability to these 2 trees, even though these areas are very similar. So we wanted to solve this problem. We did that by looking at dependency trees. So as you can see, these are the same sentences converted to dependency tree format via their head roles. So the top of the node now becomes the head of the sentence, and beneath it, directly beneath it, are its dependents. So the words that, either modify or are a subject or an object of a verb, something like that. So by doing this new format, we've eliminated the, if you look at the old trees, we've eliminated all of this non-terminal structure that sometimes you can say that it could be inaccurate or arbitrary. So we've gone to a much more direct representation, and we're also representing more directly relationships between words. So the first thing that we did here was to run the alignment, the tree-to-tree alignment on dependency trees. So to do that, we had to modify the existing program, first by allowing translation to occur at non-terminal nodes, because in normal constituency trees, all the words are at the bottom, but now they're throughout the tree. And then also to introduce a new probability, which is lexical reordering. So looking at the probability of a particular word reordering its children in a certain way and trying to see if certain words always reorder their dependents in a regular way. So after modifying the alignment program, we trained it on about 40,000 pairs of FBIS Chinese English data. And then after that, we extracted features from these alignments. A couple of examples could be the alignment score, so how probable was this alignment, and also the number of similar nodes that were aligned to each other. So here I have an example of an alignment. For every node on the left is what was on the Chinese side, and then on the right is what is on the English side. So, so we could take the probability score and use that as a feature, or look at the number of times a verb aligns with another verb. So in this example, we see one Chinese verb, but no English verb. So this feature function will get a score of 0. So this is how we work with tree-to-tree alignment. Another approach was just to look at the dependencies themselves and not necessarily the entire tree aligning. So this is something that David worked on, and it's called a dependency projection feature. So the idea behind that is that it's often seen that dependency relationships in one language are often transferred to its translation. So if word A depends on word B in Chinese, we'd like to see that whatever A translates to in English is also dependent on whatever B translates to. So the implementation that we took was to count each dependency in Chinese where the aligned English words also had a dependency. So here's a graphical representation. The top is the Chinese sentence, and each arc is one dependency link. And here is the produced sentence from the baseline MT system. And as you can see in red, there's only one transfer dependency. So it's possibly not a very good candidate. And so when we combine this feature with the baseline features, it produces actually this sentence. It prefers this sentence, which has a much stronger correlation with the original sentence's dependencies. And if you read the sentence, it's much more fluent and captures the meaning better. A second dependency feature, this is something that Sanjeev worked on, was examining the plausibility of the dependencies. So the idea in this feature function was to look at every dependency pair and say, is this a common dependency? So here's an example on the left of one candidate, which is perhaps not very good. It reads, China, 14 open border cities, construction, remarkable achievements. So if you look at the tree, we have cities modifying construction and achievements modifying construction. Probably that's not seen very frequently in good English. However, on the right, a better hypothesis, which is actually the Oracle sentence, you see China's 14 open border cities in economic construction made significant achievements were made at the top of the sentence, and these are its dependents, so much better candidate. So in order to capture this feature, what we did was to build a dependency trigram language model. So normally when you think of language models, you think going from left to right. So what's the probability of one word given the two words preceding it? So for this language model, what we did was say, what's the probability of one node, say remarkable, given its two preceding nodes, so the two nodes above it, its parent and then its grandparent. So we trained this language model on fluent English, and then extracted the probability of each dependency given its predecessor. So one concern that arose was that content words tend to have a very low probability just because they're infrequent. And so as a result, the model might prefer sentences that don't have as many content words, which is a bad thing. So the solution was to normalize the probability of each English sentence, or sorry, each English word, given the probability of its Chinese counterpart, which was extracted from the word alignments. So the second equation is basically the same as the first on the top, but now we're dividing by the probability of the Chinese. And here we have the results of all of our dependency feature functions. I actually didn't have enough time to talk about all of these. The ones I mentioned are highlighted in red. And as you can see, there was some improvement off the baseline. Some of them not as much, but some of the numbers isn't explained. So I approve this one so great.
So you were counting the number of dependencies that do make it across.
Yes.
Would it possibly work better to count the number that didn't make it across? What I'm concerned about is, suppose you've got sentences that get longer and longer, then you're rewarding them more and more. Whereas you might want to actually have a feature which just penalizes mistakes.
That's another approach to take.
Although it seems true that features that correlate with sentence length tend to help the training because of the length penalty.
Right, this one seems like it would correlate positively with sentence length, and you want one that correlated negatively. Oh, I'm sorry, no, that's right. But nonetheless, the style of the projection features here is different from the style of projecting the part-of-speech features that you talked about, where you say, well, if you had so and so many in the source, then what would you expect in the target?
As well as features that didn't make it in, where you try and where you train the probabilities that certain kinds of dependencies will make it across in certain contexts, and then
conditioning on the label, on the relation.
So I hand you to Luke.
All right. So we're now at the last set of feature functions, something that has been dubbed tricky syntax. So what does that mean? So these are syntax-based alignment features, but they do not align the full parser. So this was quickly dubbed to the one word tricky earlier on in the workshop. I'm Anup. I'll talk first, and then Brian Jain, who's our third undergrad from UPenn, is going to talk after me. So these are the three feature functions I'm going to talk about, and then Brian following me. The first one is about using the evidence from the parser in order to help score the alignment template bound. So let me remind you this slide. So previously we were just checking whether certain alignment templates were right continuous, left monotone, and so on. Now we'll use additional information that we have. So in this case, we have a certain output from the parser over this English output, and each of these constituents gets a log probability. And what we're interested in doing is looking at the boundaries between alignment templates for which the baseline system has little evidence, but relies on various language model features. And to take the evidence from the parser probabilities in order to score it. So this is a very simple model. All it does, it checks at this point how many constituents span across this boundary. And it picks a minimum probability that spans across this boundary. So in this case, the minimum parser probability here is this probability for the NP, and so on and so forth. So the one here would be this NPB here, this probability. And now the feature function is simply going to be the sum of all of these minimum parser probabilities, and you get a single number that's going to be the score for this sentence. And then we're going to compute, using the rescoring method, a parameter for this feature function. So this is the feature function that is described here. So that's clear. Move along. Go to the next set of features that I'm going to talk about. And this one involves actually trying to make the full parse tree alignment models tractable. So essentially, we're going to look at hacking up the parse tree, or in other terms, trying to find some kind of Markov assumption for full tree alignments. So this is what we have as the full information that's given to a full parse tree alignment model. So we have the Chinese sentence and the word alignments that are given to us by the MT system, and we have the parse trees on either side. So I apologize for all the various positions I'm putting these parse trees in, sideways and upside down and so on, but this makes it all fit in us. So now we want to be able to exploit this information in order to do alignment. So you can think of it as somewhat trying to compute a tree edit distance between them, and there are various models to do this. Unfortunately, they have certain problems. They're very expensive to compute for long sentences and trees which have very flat constituents, so the fan out is very large. There's also limited reordering in the embeds list. So you don't observe, by reordering the top level of the tree, you could radically change the order of the constituents. But in the embeds list, we don't have any such reordering. So it seems like a waste to try and do this over the full nether regions of the parse tree. So what we came up with after introspecting on these embeds lists for a while is a very simple algorithm for hacking this full parse tree into tree fragments, wielding a large machete across the parse tree. What we do is we start with the word alignments, and we have two parameters: the maximum number of words we want in the fragment, and the maximum height of this tree fragment that we will accept. So it just goes left to right across the Chinese, and let's say that we accept at most 3 words and a height of at most 3. So when it goes past, so the first Chinese word aligns with these 2 English words. This induces a tree alignment between these 2 fragments automatically, because these are the ones that are the minimum spanning. If you add just one more word, what happens is you're forced to take this entire NP aligned to this entire NP, and this violates our maximum height criteria. So what we do is we take this tree fragment and then continue on with the Chinese sentence. Okay, so essentially what we do is we are trying to find a cut through this tree. So the example I gave you for n equals 3, which is the number of words, and k equals 3, is just for illustration. So in the experiments, we actually use n equals 9 and k equals 5 to get reasonable size fragments.
Excuse me, just again, sorry to poke this up, but you're losing me again here. This is all being done on the training data. so you can align the two sets of parse trees in some intelligent
So
fashion?
this can be done in both the training and the development and test. So in this case, actually, for the more complex tree alignment models, they were already trained on the full training data, but they couldn't be applied. The training data was about 60,000 sentences, but the dev and test were millions of sentences. So this was an easy way to speed up the operation on the. You didn't need to actually re-estimate. You could. It would be a better model that way, but we didn't do that. So you could do this both on the training and on the test. So what's the advantage of this algorithm? Well, what you now have is actually a full parse tree alignment model, but on these sort of little parse trees, and then you can just combine the score as a simple Markov model. The advantages are tractability, so it actually enables some of these more complex models to cover 98% of the embedded. And it's also more robust to bad parses, so certain fragments might be worse than others. This lets you get around this problem. So what happens when you apply this? So this is your input to the algorithm, and when you apply this very simple algorithm for hacking into tree fragments, this is what you get. So each of the, these are the two parameters, and these are the tree fragments that you get for this very limited case. So remember again, these are very small tree fragments because these parameters are small for reasons of illustration. Now, given this alignment between tree fragments that was bootstrapped out of the word alignment, we can now compute a feature function that actually takes a more complex full parse tree probability score and uses it in a very straightforward log linear fashion. So it takes a frag 0, runs it through the tree to string model, and you take that score, the log probability of that score, and then you add it to the score for this fragment and so on. And now this will be the score, the feature function that will score this entire sentence, this entire sentence in the investments. Okay? Finally, what I'll talk about is yet another method for hacking up parse trees, but this time in a previously known way. And we'll use this same idea to score now word alignments rather than parse tree alignments. So when you look at this parse, this is the same parse I showed you earlier. There is some additional information in the parse, which I did show you. That is namely the head and the argument information. So the parsers naturally compute this information. They try and find whether the VP's head is a VB, and the example I've shown here, just in case the color didn't show, is marked with the -H. So VP -H is the head of this IP in Chinese, and this NP-A is an argument sister of this VP. So now you can see that every node at least has one blue dot, right? That's its head dot. And the same in English, you have every node that has at least one blue dot. And there are some cases where there are these red argument nodes. Now, obvious thing you can try is actually recover, so you can store the information about these other connections. So there is this privileged connection between this IP and this VP, and there is a non-privileged connection between this IP and this non-blue dot. So I'm just going to remove all the arcs that are not between these non-privileged arcs, as it were. Yeah.
I just ask a detail. Why is that possessive blue? The acid Chinese.
Oh, this one?
No, down in the English.
Oh, yeah.
In the English, the POS. The possessive.
The bottom.
Down.
China.
Down.
Here.
That. Why is that blue?
Because it says that this is the head word of this NP.
And I should agree with that.
No, you shouldn't, but it doesn't matter. As long as it has some head order I don't really care. So that's, yeah, it might be making a mistake in this case.
Okay.
Or it might be that the tree bank is wrong and you don't agree with it.
Okay.
Right.
It might be a strange syntactic view.
So this is tricky syntax, you know. I'm trying to trick you.
Typically, progressive snappers
Is that right? Okay. Just a minute.
Okay.
it works better.
So let me just do the kind of animation that people who use LaTeX can do, which is go back and just show you what I was doing, is just removing all of those things that don't connect to a blue line, right? And there's one other thing we do is split out these arguments. And now if you notice when I just did that was every word has a tree fragment. We know exactly how to compose the original tree, but we actually don't care about that for this purpose. But what we do care about is that every word gets at least some tree fragment from the original parse tree. So in this case, this VD is headed by this VP, is headed by this IP, it has an empty argument, for example. And similarly for the English. And let me just sort of clean up the tree drawing, and what you get is one tree per word for this entire sentence. And in addition, you have word alignments. So these objects are called elementary trees and are sort of objects that are part of grammar formalism called tree adjoining grammar. And these, who's laughing? I was hoping for a laugh. One is good.
But not at that point.
I'll take it. So now what we have is actually word-aligned lexicalized trees. So by lexicalized, I mean there is a word at the boundary feature. So now we can compute models based on these kind of word-aligned tree fragments. In fact, we tried several models. All of them were trained using the SRI language modeling toolkit using 60,000 aligned parse trees. So we started with 100,000, of which 40% did not get parsed in Chinese. So we were limited to this. If you're curious, the total number of elementary tree templates, that is the tree structures themselves without the words, was about 13,000 each for Chinese language. So it's not that much. But they are larger than part-of-speech templates. So one simple model over alignments. So by model over alignments, I mean we start from the Chinese side and then we score each of these alignments in turn using submodels. So you can think of it as a language model over alignments. And a simple one is a unigram model. So you have the foreign word, its tree, the English word, its tree, and these are aligned, and we score each of these alignments. Actually, I cheat here, so these are actually could be many to one or one to many, so you count them all together. So it's very sparse. Another way to score these models, score these alignments, is by using a slightly more complicated model where the English lexicalized tree is generated conditional on the Chinese one, and then the subsequent Chinese lexicalized trees generated based on the previously aligned Chinese elements. And in addition, we actually also tried IBM Model 1. Kenji tried IBM Model 1, which is the sum of all alignments using these basically lexicalized elements. Any questions about that before I show you some?
Is the dictionary over words or over trees?
It's over lexicalized tree fragments. So elementary trees include the words in them by definition. So here are some blue numbers. And so the baseline, in case you're tired of asking it every time, is 31.6. Scoring using the parser probability to score the alignment template boundaries does actually pretty badly. And, just using the original alignment alignment template probabilities of whether they're left monotone or right continuous actually does much better. So that's depressing. But what is encouraging is when you try the tree-to-string model without our machete, you get 31.7, but that covers only a small fraction of both the dev and test because of the complexity. And with our machete tool, the tree-to-string model does get subsequent significant improvement because it can cover more and it's more robust. Model 1 on elementary trees takes 31.6, exactly at the baseline, and the various more complicated models actually get 32, which is notable also because it's a less complicated model than full parse tree alignment. And if there are no more questions, I can pass you on to Viren, who will also wow you with additional marvels of the machete. I promised myself I would say machete at least 10 times.
So I've been looking at additional features that exploit parse trees in both the Chinese and English side, as well as the Chinese to English word alignments given by the MT system. And the basic idea is that we'd like to keep things that are related in the Chinese side together, keep them detected rate on the English side. And so we'd like to develop a measure of that so that we can analyze sentences where this isn't true. So two basic features that came out of this idea was, first of all, a tree to string penalty. So this one does not look at the English tree, and instead it looks at the Chinese parse tree. And the way it works is by going through the Chinese parse tree, and for each constituent, considering the Chinese words under it. So here we have an NP, and we have a couple of words under it, China's 14 border open cities. And we look at what those align to on the English side. This is the corresponding one of the English translations. And they align to those blue words there, but not the red one. And we look at the leftmost and the rightmost blue word and see if there's anything between those two words which weren't aligned to something in the original Chinese subtree. And in this case, marked was not, so that incurs a penalty. And for each Chinese constituent in the parse tree, we simply make a binary decision of whether to incur a penalty or not, and then sum those penalties. And a related model is a tree-to-tree penalty, which, as in the previous case, looks at each Chinese constituent and the words under it, looks at what they align to on the English side, and then using the algorithm that we've described earlier, tries to find the minimally covering subtree of the full English parse tree that covers those English leaves, which were aligned to the Chinese words. And again, we see if there's any words within the English subtree, here this VP, which weren't aligned back to words in the Chinese parse tree. And in this case, remarkable was not, so again, we incur a penalty for this sentence. And we do this for all the Chinese constituents and sum a penalty. A slightly more complicated model tries to use some to learn some relationships between Chinese and English parse trees. So on the top here, we have a Chinese parse tree on the left side, an NP, consisting of order open cities, is the English gloss of those Chinese words. And then we look again at what those words align to on the English side and find a minimally covering subtree, English subtree, that covers those leaves. And we have this VP, open remarkable border cities. And what we'd like to do is calculate probabilities of stuff like the probability of seeing a VP subtree given a Chinese NP subtree. And of course, to do this, we need some training data. So we use roughly about 50,000 sentences, which were parsed. This data set, which Anu referred to. I think it was actually close to 50,000, I guess. And we just estimate these probabilities. So we count up the number of times we see an English VP subtree given a Chinese NP tree. And it's important to point out that we don't explicitly have these relationships, even on the training data, between Chinese parse tree constituents and English parse tree constituents. So we use this algorithm of using the alignments and minimally covering subtrees to assume that those are related subtrees. So in this case, for example, the probability of seeing a VP subtree given a Chinese NP is 1.9%. The probability is 0.01, so we'd like to multiply these probabilities across each Chinese constituent and then use that as a score for the English candidate sentence. And there's additional features based on this idea. For example, the number of words in the English subtree given the number of words in the Chinese subtree and its label, and so on. So here's some numbers. On the top, this is a chart that reflects numbers from the training data. So this isn't. This is supposed to reflect really the quality of information that we've learned from our training data. So this tells us a few things. One thing to note. So we've listed 3 examples here: a CC, VP, and an IP. And a CC is essentially a part of speech tag. It's very low level within Chinese parsing. A VP is a little more higher level, and then an IP is supposed to be basically the equivalent of an S in an English parse tree. And we can see that our intuition is more or less respected with the CC in that Chinese parse trees with a CC label get translated to English CCs 84.5% of the time. And with the VPs, things get a little more strange, with VPs translating to MPs 32.7% of the time. And this could reflect either noise in the data or linguistic differences. And with the IP, things are very strange, with entire sentences being aligned to NPs most often 48% of the time. So there's a couple of things you could say about this. One is that there's extremely noisy trees. The other is that the assumption of aligning leaves and finding newly colored subtrees is not valid, but it's not entirely true yet. And these are just some results. So none of these features really had a particularly large impact, which could be reflected by these numbers for our training data. And so, what's next? Any questions?
Are you the first of our undergraduates?
Yes, I'm the third of our undergraduates for this section.
During the workshop, we have also tried other re-ranking algorithms designed to balance the minimization algorithm. And an obvious candidate is the class of discriminative machine learning algorithms. And we first tried to support the vector machines at the beginning of the workshop, and it's kind of too slow for this task. And we have tried to use variants of perceptron to re-rank the translation results. And the underlying assumption is that if we can find a hyperblend could successfully separate the good translations and the bad translations, then the distance to the hyperblend could determine the quality of the translation, which means that the direction of the weight vector is in the same direction of the score matters. And the good news, the advantage of using those class of discriminative learning is that we can use a hooded dimension space, and with that we can use individual syntactic structure as a feature. And this method has been shown very useful in parsing ranking. And the problem of use this machine learning algorithm to the translation ranking is that actually in our test set we have in our data set we have 993 Chinese sentences, and each has 1,000 English translations. Actually, this is inseparable with the baseline features, even with 100 or more features, it's definitely inseparable. And in order to handle this problem we have is first we tried two checks. First, that we do not use all the translations in the training, which means that in that 1,000 and best, we only use, for example, top 30% and the bottom 30% of the translations. According to some score like delta blue score, liquid score, we hope to find a hyperplane between them. And we have also tried use the so-called lambda check, which means that we insert a new dimension for each translation, and this could promise that we can find a hyperplane. And this didn't work. The reason is that we need different bias for each Chinese translation. The idea is like follows. For example, we have a two-dimension space, and then those are the English translations for Chinese sentence 1. Each dot represents a translation. Those are translations for the second Chinese sentence, third, and the black dot represents blue translations, and white represents red translations. And obviously, we are unable to find a hyperplane could successfully separate all the black points and all the white points. However, we can find a set of parallel hyperplanes that could successfully separate good and bad translations for each set of translation.
I can ask a technical question. How do you vectorize these sentences?
We use a set of features to represent an English translation.
Like what?
I will say how do we do that later.
In principle, all the features you heard of up to now in the last hour.
So
All 450.
So in the baseline, there are these 12 feature functions, and then each sentence is basically a 12-dimensional vector. And anything that the learning technique sees is a 12-dimensional vector. And then if you use additional features, we have 15 dimensions, 20 dimensions. It's always basically a vector of numbers. Feature functions are, in the end, nothing else than numbers.
And what you do is you're changing the weighting on the feature functions to try and get the better translations to occur at the top after you have your basic feature model.
Right.
And actually, I will explain later, there were two kinds of features. One is the style of the features that we have developed during the workshop, this kind of comprehensive features. Another class of feature is just to use individual syntactic fragments as a feature, which I will explain later. And the idea is that for each Chinese translation, we need a distinct bias for them. And actually, we have used two algorithms to handle this. The first is commonly used in machine learning task, which means that we use pairwise translations as an example. For two translations, Gij and Jk for the same sentence I, then we say this pair is a positive example if Ij is in the top percent and the T of Ik is in the bottom percent. Then we produce a re-ranking problem into a classification problem. And we can actually use some implementation. We don't need to use samples explicitly. However, this method violates the independent assumption because we have 300 good translations and 300 bad translations, and each translation will be used in 300 samples. This is really bad. And the algorithm we used in our research is so-called multi-bias perception algorithm. And the idea is that we train a weight vector for all the English translations, but we train a unique bias B of I for each Chinese sentence I. And see some detail of the and the input in the translation is of Ij. I is the ID of sentence. We have S Chinese sentences. And Y of Ij is positive 1 or negative 1. And the output is the W, is the weight point of the husband. This is hopefully the direction of the score metric, and then there were a set of internal variables, those set of bias for each Chinese sentence. And the updating is similar to the traditional perception algorithm. The only exception is that if we cannot successfully classify a sample, we updated the bias. We only updated the bias corresponding to these English translations. We don't touch others.
And again, just to clarify, you have a vector of 12 scores. You have a set of weights, and you're only learning these 12 weights in this, basically. And then that's supposed to cover every. There are no additional parameters that are being covered.
In the baseline system.
In the baseline, yes.
But this is not baseline.
This is, we tried both. Actually, we have the experiments. One is to use these 12 baseline features. And this is one set of experiments. Another set of experiments, actually, we extract the individual structure from the for example, path trees and something like that. Then the space width is very large. And it could be shown that it converges after several steps, and we can give a lower bound of the margin and give expected risk according to the margin-based bound. Now we have two sets of experiments. One is to use the features that we have developed in the workshop, and actually we use the 30 best features that we have developed. And the baseline at the beginning of the workshop is 30, and we get blue score of 31.6 with perception of that, and this is really not a good result. And the reason is that we think the discriminative learning is not a good algorithm for the data set we have been using because we have a huge FS list and a very small number of Chinese sentences, which means that it's more like a regression problem, and we cannot get a large set of samples. And this is not good for the discriminative learning. And another set of experiments is to use individual fragments of syntactic structure features. And since we need to use good translations and bad translations, then we can only try on the depth set, which means we can only use the non-necessary Chinese sentence. So this limits the use of many useful features. For example, we cannot use lexical items. It definitely gets rid of overfitting to the depth set. Anyway, with this permanent setting, we get promising results.
Can you go back? I must have missed something. Why is there a small number of Chinese sentences? Don't you have, like, you have 800? The deal is it's only 800 sentences in the dev set, and that's what you're training on, and that's too small.
In the development set, there are 993 sentences.
Okay.
And for each of them, there's a large number of indexes, but that's always for the same sentence.
Okay. I mean, another. Okay.
And we have used two set of those individual features. One is to use pair of and pure sequence in a large template. And the feature space is 30,000, and averagely 31 actual features for each example. And we get a very high blue score on depth set, which means that this is very discriminating. And the blue score on the test is not bad. So it tells something like it's in this way, those individual features are very discriminating. We hope if we have a large training set, we may get better results. And another set of experiments is to use the fragments of past trees of the English translations. And in the previous one, we used alignment information, but for this, we only use the features from the English sentence. And it's the space. And we found that actually we even can get good blue score on the depth set, which means that it's very important to use alignment information in the training. And we can imagine that now we have only used 993 Chinese sentences, and if we use, for example, 100,000 Chinese sentences, then we can use more individual features like lexical, like items and elementary trees. And for each one, we have 10 good translation, 10 bad translations. And we, in this way, we will get better.
Do you have any feeling, when you say, I guess the proposal will come later, but you think you can get away with only 10 good and 10 bad ones to get decent perceptron type learning?
And the good question, and this actually, this is a tricky question problem of how to select those 10 good translations and the 10 bad translations. If these 10 good translations are like each other very much, this is very possible, and maybe it's good sample selection methods. And the idea, as I have talked with friends, that we just select 10 good from, and for that 1,000 events, and then you use some heuristic rules, and we hope this will work. Yeah. The next is Sean.
There are some questions while Shankar is getting set up.
My understanding that is you try to update in each iteration, try to update the bias of the separated plane.
We update both bias and weight vector.
So we do not assume that the separating plane has the same direction. Okay.
How are the bias used in translation?
Being translated? And actually, the re-ranking problem is don't need a bias for in the test, because for translations of the same sentence, they use the same bias. Yes. So the bias is not part of the algorithm. We are only interested in the direct. Actually, we are only interested in the weight vector, but the bias is not used in the test.
So during testing of different sentences?
Yes, we have different, but we only do the same sentence.
So hi. So far we have been looking at a lot of this training techniques, which based on features, both with maximum blue training and also perceptron. These are feature-based training techniques. As opposed to this, now I'll describe a discriminative search technique, which can integrate loss functions. That's the minimum base risk approach. So the title is minimum base risk decoders for machine translations, where I will also look at specifically incorporating syntactic structures via loss functions. So some of these ideas we sort of laid down in a framework before the workshop, so I'll first present the framework and then I'll describe it in loss functions. So a quick overview of the minimum base risk approach to decoding. So minimum base risk decoders have been used in the past for many speech and language processing tasks to optimize task-specific or application-specific performance. So the best description of this comes from ASR, but let me give you a quick description. So ASR can be viewed as a classification problem where you take acoustics and classify acoustics as a word sequence, a sentence. So that's the ASR as a classification problem. And the conventional decision rule in ASR is a map approach where you pick the hypothesis with the maximum posterior probability given the acoustics. Now, the performance measured in ASR is, however, not sentence error rate but word error rate, which is measured by the Levenstein distance between word strings. So there is a mismatch in the decoding criterion and evaluation measure, and MBR, minimum base risk approach, attempts to rectify this difference or the mismatch, and the main procedure is to obtain the expected conditional risk of each hypothesis. So risk is computed as an expected loss. So the expectation of, so you take each sentence hypothesis and compute its expectation according to a loss function. Loss function is usually the Levenstein distance. And as a second step, you want to select the hypothesis with a minimum conditional risk. So you go over, you find conditional risk, and you select the hypothesis, and finding the hypothesis with the least conditional risk is equivalent to selecting the hypothesis which is most similar to other hypotheses. So this is a form of consensus decoding, where the consensus is in fact measured by the loss function. So this is the scenario in speech. So moving on to MD, our goal here is to design decoders which optimize translation qualities under various performance metrics, which in fact measure some aspect of the MD translation performance. So as opposed to the discriminative, as I said earlier, it's a discriminative search criterion as opposed to a training criterion based on feature functions. So the setup is as follows. So we have a baseline translation language model, in this case baseline system from ISI, which can give us scores, which is the joint probability of, which is the posterior of a translation and its alignment. So lowercase e is the English sentence, a is the alignment, and f is the Chinese sentence. We have a set of most likely translations of the Chinese sentence, and each hypothesis in this set contains the sentence, its alignment with the source, Chinese, and also a tree. So these are the three sources we have. In addition, we also assume that we have a parse tree for the source sentence, in this case the Chinese, and a loss function, which in fact can compare. So given the fact that this EAT, the first argument here is the reference, and the second is a candidate, it measures the quality of a given hypothesis with a reference based on information from alignments, alignment, word sequences, alignments, and the parse trees. So given the scenario, once again the decoder, the minimum basis decoder, optimizes or minimizes the conditional risk, and in this case the risk is measured by this generic loss function. So in this workshop we restricted ourselves, so there are two aspects in this decoder. So one is this computation of this expectation. So this, for this workshop, both this computation of expectation, that is this summation, as well as the search, was restricted to the candidates in the n-best list. This is quite tractable and allows us a lot of experimentation with a variety of loss functions, which I will describe now. So there's a hierarchy of loss functions that we developed during the, so these were formulated earlier, and during the workshops we were lucky enough to find resources to be able to implement these loss functions. So these loss functions grow, as we described earlier in the talk. These loss functions grow in complexity of the level of syntax that they incorporate. So the first level of loss function is one where we don't look at any parse trees or word alignments and just look at the strings. So the loss, in fact, between n and the hypothesis just simplifies to a loss between the word strings. And examples of such loss functions include the sentence level blue. The sentence level blue is the one, it's just the same log linear combination of unigram, bigram, trigram, and 4gram precision, except that we smooth to avoid zeros in case any one of the precisions happens to be zero. Word error rate, which is the thing from, which is the usual Levenstein distance, and position independent word error rate, which doesn't ignores the positions. And so these are the three loss functions that I did in this, which fall in this category. So just to see some examples of the minimum based risk hypothesis under these loss functions, here are two examples. So the first one is an example of an MBR hypothesis optimized for blue. So this is the produce, which reads as follows. So last year the Japanese commodity exports $8 billion, representing the growth 10.9%, import of primary products $1 million, up 4.4%. And the MBR hypothesis essentially quite similar, except that we get this nice trigram, nice n-gram, which is up 10.9% than the previous year. So in fact, MBR by its consensus mechanism is able to come up with a hypothesis which is better in terms of blue, where blue measures the consensus in terms of.
I'm not sure how this works. How does this work when there's no word alignment? How do you look across hypotheses if you have no idea of, it seems you have some form of word alignment.
So here, at this level of loss function, we don't look at the alignment. I'll describe later. But right now, it's the, so blue takes a hypothesis and a reference and computes precision between them. So I'm just turning blue into a loss. So blue just looks at, so given a pair of sentences, looks at unigram, bigram, trigram, and 4gram precisions and computes a log linear combination. And there is no alignment in that. So the loss function here is just it measures, you can say, precision loss in terms of blue.
I guess I'm used to seeing this in speech recognition. Right. What you're effectively doing is you're combining information across different hypotheses. So I guess I don't understand how, when you have two sentences in an n-best list, how these things would be combined with the measure that you're describing.
So, so going back, so just to clarify what I'm doing.
we would like.
You're not, you're picking
Yeah.
one out of an invest list.
You're just picking it,
Yeah.
period, okay, so it's not like the speech consensus in this case.
The original one was for invest list, now it's for last, but this is before.
So here the choice would be as this basically one out of the invest list. So the search space is not expanded beyond what is there in the invest list. So looking at the different loss functions like position independent error rate, which completely ignores the word order, we see that the MBR hypothesis is in fact not very great. It's even worse than produced in terms of its fluency, but probably it gets this word prime minister correct. In this case it does, because I know that this is a sentence where the MBR hypothesis is better in terms of the criteria. So the consensus can be in terms of different loss functions, but the idea is that that helps to improve the consensus in terms of the desired loss function. Moving up the hierarchy, we next look at target parse trees. So we still assume that we don't have alignment. So the loss function between the reference and hypothesis simplifies to a loss between their parse trees in both languages. So we are looking at the parse trees. And the loss function which we thought was interesting was this idea of tree kernel of Collins from last year's GMNLP, where the idea of a tree kernel between any two trees is to compute the number of common subtrees between the two parse trees. So in fact, each tree has a very high dimensional representation, and this tree kernel computes a dot product in that representation. So these are T and T prime, and this is a dot product in a where this could be a very large dimension. But the nice thing about it is that this computation is practical, and in fact it is very efficient via recursion that Collins presented. So this metric, loosely speaking, measures the structural similarity of the parses of two translations, once again ignoring totally the alignment information given by the MD. So we looked at the MBR is done under this loss function, and in fact the output generated by the MBR decoder, we found that there were 14 sentences which were not parsable, i.e. they were assigned a probability of 0. In contrast, there were 29 sentences in the baseline system output that were not parsable. So going by this, we can say very loosely, or very non-linguistic way, we can say that the MBR hypothesis probably improves the grammaticality of the hypothesis, as measured by the number of sentences that are parsable. So once again, if we look at some output, the output, so here is a produced output, this here the leading row still prominent. The MBR hypothesis says this is a very important row. So these two aren't that, so the output is not meaning preserving, but that it shows that translations become more fluent. This also is reflected in the fact that we don't have alignment information here. So, and the idea is here measuring some consensus with respect to tree structures. So, but the interesting feature about this loss function is still the fact that we get fluent translations.
But is it right or wrong? I mean, should year be in there?
Well,
Should it be less fluent but have the word year so that whoever's trying to read it knows it refers to some dependency on what year it is?
So it depends on your criteria of judging translations. Clearly, if we want content, this is not the loss function. But the idea here is just to come up with the loss function which probably tracks fluency better. And next, I will soon follow up with a slide where adequacy will also become important. But the question is right. I mean, it depends on our criterion of judging the translation. In this case, I'm just saying that let's focus on fluency. So now comes the top level tier in the hierarchy, where we use the maximum resource of the maximum availability of resources in both languages, namely source and target parse trees and word-to-word alignments. This closely follows from the work of Viren and Anu, which we described earlier. So the problem is this. So we have a Chinese parse tree. I have replaced Chinese words with their indices in the sentence, and you have two translations in invest list. So this is a produced, and this is maybe something. This is the top candidate number 1. And this is some other candidate in invest list. And what we have are node-to-node alignments between the Chinese and the English trees. This is obtained using the approach described by Viren, where we use word alignments on the leaves and use minimum spanning ancestor to find the node which covers these leaves. So these node-to-node alignments were obtained by not a tree-to-tree alignment procedure, but in fact a procedure based on word alignment. So assuming that we have this structure, the idea is now to come up with a loss function that makes use of this structure. So this is joint work with Viren. And the form of loss function is now involving all the variables that I put up in the first slide. Namely, we have English center, so we have the reference consisting of the reference, translation, alignment, and a parse tree. And so the hypothesis also has a translation, alignment to the source, and the parse tree. Plus, we have the source parse tree as well. And via the alignment, we have each node in the Chinese tree mapping to nodes in the mapping to two different nodes. So this node NP in this Chinese tree maps to this NP in this English tree, and this NP in this other English tree. And similarly, this VP goes to this VP, this tree, and this VP, this other tree. And now the loss function is essentially marching through the nodes in the source parse tree and comparing the subtrees which are rooted at these nodes to which the source node is aligned. And the only loss function that I tried out was a simple 1-0 loss function where the loss is 1 or 0 depending on whether or not these subtrees are identical. So going back to the example again, so we see that, so if we are sitting at this node in the Chinese tree, these two subtrees are in fact identical, so this loss would be 0. Whereas if I look at this VP in the source tree, this subtree rooted at this node is clearly different from this, so here the loss would be 1. So it's a very simple loss function, except that I start from the root in the Chinese tree and go along all the rows, all the interior nodes, and for each interior node makes a comparison between the corresponding subtrees. So it's an interesting loss function, and an example output, so the MBR hypothesis shows that output achieves better fluency and even better adequacy to some extent. So let's looking at this produced, this is an example. At present there is no organization claimed responsibility for the attack. The MBR hypothesis reads at present no organization claimed responsibility for the attack. Of course this is a good example, but it seems to suggest that the procedure is working to some extent. So here are those were examples, but we are interested in averages and results. So these are the performance of all the decoders so far. So this is on the test set, and the baseline is the baseline from ISI. So the baseline, so going across the columns, we have the different performance metrics, blues. All these first three metrics are percentage, expressed as percentages. So blue, multi-reference word error rate, multi-reference position independent word error rate, multi-reference parse kernel, and multi-reference byte tree loss. So these two are just based on the metrics I defined. And going down, first we have the baseline, which is 31.6 in blue and other things on other metrics, and the MBR decoder optimized for a loss function. So the interesting thing is that under each loss function, the MBR hypothesis performs the best, with only one exception, that the byte tree loss, which I showed, just improves on word error rate better than a blue minimum basis candidate based on blue. A minimum basis decoder optimized for the word error rate loss function. This is an interesting thing which I would like to look at it later, but this result I got it just yesterday, so I don't have much time to analyze it.
Just to ask a question again, these seem to be more or less in the same order of magnitude of improvements that all the other people seem to have found, but there's some implication based on the previous foils you've had that you somehow think that this is genuinely giving you better fluency. Is that just because you showed us a couple of good examples, or is this actually sort of happening even if the translation is less accurate?
So I showed you good examples to answer the first.
So sometimes it does terrible.
Yeah, it does terrible. So this
okay.
is on an average. Yeah. But the examples were just to show that maybe this is doing something which is interesting and just to sort of hope for a better metric maybe. But so that was the baseline. Now we also show that, so we had a best system as of the fourth week of the workshop with the maximum blue training with bunch of feature functions, and doing an MBR decoding on that furthermore improves it. So the best system at the middle of the fourth week was 22.9 in the blue, and doing an MBR decoding further brought it up to 33.2. So we can always improve on a good system which has been trained with a discriminative training procedure, because it can also always be applied, and which is an interesting aspect of this.
Was this a tier 2 function? I can't remember what you said. This is tier 2
Yeah,
version?
this is the, which one is
Yeah.
well, this is the tier 0, but
Oh,
the
that
tier,
was tier
this is
0.
tier 1 and this is tier 2. The pass kernel is tier 1 and the likely loss tier 2. While they not necessarily improve on blue, they improve on their own metrics with respect to it. So in conclusion, MBR decoding allows translation process to be tuned for loss function. So given a loss function, we can optimize that loss function and get a good performance. On the top of a good system trained with the maximum loop procedure, a minimum base risk rescoring furthermore improves the performance. So we can expect to get performance improvements on the top of a system that has been trained. The development, there's an interesting set of loss functions that we have developed that make use of syntactic features from English and Chinese parsers and word-to-word alignments. The topmost tier seems to be very interesting and sort of maybe needs further research. The minimum-based risk decoder is based on a sentence-level loss function. So, in contrast, blue and other metrics are holistic in that they look at the whole test set. So, the fact that we can optimize based on a sentence-level loss function clearly highlights the need for a sentence-level evaluation measure, which would be very interesting. In future work, we would like to look at loss functions based on tree-to-tree alignments. This is the work by Dan, and we would like to see that those can be incorporated as well. We would like to perhaps constrain the search space of the decoder to only the syntactically plausible translations. This would be an interesting way to see if outputs are more syntactically plausible. And as in speech, we would like to see using word graphs for minimum-based coding would allow us to explore a large search space and get further improvements. So, thank you.
Perhaps a comment rather than a question. You're improving, you're searching for better and better loss functions to improve the quality over maximum likelihood solution. So when the maximum likelihood solution is not the correct answer, that casts a doubt on the goodness of the underlying probability models. Perhaps they're deficient, and perhaps we should also look at better probability models.
Yes. Yes. Okay. I guess the problem here is that was a comment, I suppose. Right? So
we are running somehow.
Okay.
You're done.
Yeah, I'm done.
Behind, and we wanted to have the break later, but maybe we should take the break right now and be back here at.
Maybe we can make the break by 10 minutes.
Okay. So 12:10.
No. Lunch is after we have 2 presentations to do and then lunch.
There's going to be one more presentation and then 2 proposals, right?
And then conclusion.
Yeah. Okay. Thank you. Please, I will urge you to come back.